A warm welcome to all participants to our virtual presentation of the Bosch Engineering high-performance hydrogen engine demonstrator. My name is Stephan Tafel. I have worked at Bosch Engineering since 2014, becoming Vice President in 2016, and now I'm responsible for development vehicle cross-domain. That means responsible for the integration, calibration, validation and verification on vehicle level. And that includes also our test benches, our test center. I will give an overview about our development journey and what we learned along the way. Many thanks to my co-author, Lionel Martin. He is our passionate product manager for the hydrogen engine. Our ambition for this project: analyze the potential of CO2 neutral and high-performance powertrain with equivalent emission of a classic powertrain, of course by using hydrogen out of renewable energy. Enable an acceptable market entrance by adapted conversion of a series gasoline engine to hydrogen fuel. With integration of all related systems for propulsion and storage in a race car, which could maybe target 24 hours of Le Mans. And at least to demonstrate our ability in a complex vehicle cross-domain project, including all system engineering for a sport or a race car. In front you see a design study of our demonstrator. Important to say, on a test bench you prove a concept. Emotion will be released by real driving it. We are very proud to cooperate with Ligier Automotive, a famous French race car manufacturer who is also fascinated in integration a hydrogen engine in a competitive race car. Now coming to the beating heart of the project. Base is a 3-liter B-turbo gasoline engine, 6 cylinders in a 90-degree V configuration in volume production with 463 kilowatt at 7,500 revs and a maximum torque of 730 Newton meters at 3,000 to 5,500 revs. One goal: to make as few changes as possible for the existing engine. And that we see here. We use specific injectors for hydrogen, of course, DI and hot fuel. Then we adapted water injectors. We used ignition coils and spark plugs specific for hydrogen. We dethrottled the exhaust line. It's clear because for a race car, and we had no modification of the combustion chamber, of the cylinder head, turbocharger, crank or body engine. We used a Bosch control unit, which is on the platform development for hydrogen, and we added specific function for the car. We spent around 350 hours on our hydrogen engine test bench for the engine control. And that includes the full map engine calibration and also what we need for the vehicle calibration. We optimize the water injection strategy and the engine response, and I will come to this a bit later. Then the recognition and strategy for the irregular combustion or pre-ignitions, and of course the specific hydrogen safety strategies. On the top right you see the performance map with 443 kilowatts at 7,250 revs and 650 Newton meters torque between 4,000 and 5,000 revs, which is really a great achievement with the original combustion system and the series turbochargers. Looking a bit more into the cylinder setup, you will see on the next page the cross section, which shows the orientation of the injectors in the cylinder head. And I start from the combustion chamber. First, the hydrogen piezo direct injector with outward opening valve. Due to the hydrogen specific chemical properties, its volumetric density is very low compared to gasoline. This leads to the challenge that during the relatively short injection time at high engine speed, the piezo injectors were not able to deliver sufficient mass of hydrogen. Therefore, 2 PFI multi-purpose gas injector per cylinder were added in the inlet ports. They are still in an A sample of our future H2 injection generation. To lower the combustion chamber temperature, series water port injectors, EVWE, with double cone spray came into play. The position of the water injection was defined on the basis of dedicated spray analysis and simulation. Finally, the hydrogen ignition coil, free of residual spark energy to prevent post-ignitions, and spark plugs rather cold and without producing to prevent pre-ignition. To optimize the combustion and power, the three injection systems were activated individually and partly combined, which enables effective implementation of different engine operation strategies. These all gave us really a good engine performance. Here an insight of our investigations and limitations to the maximum performance. On the top right, the map of the corresponding brake mean effective pressure values in relation to the engine speed and relevant limiting factors for the mean pressure. I start with a direct injection. The available injection window must be fully exploited. However, starting injection at an early stage must be avoided due to the high pre-ignition tendency. This limits the injection window and it doesn't reach the required fuel level. So we reached only 280 kilowatts. We introduced water injection, which cools the charged air and reduces the temperature in the combustion chamber. The pre-ignition tendency was limited and the injection window could be extended across the entire speed range. Still insufficient mass flow rate for the required fuel level, and we reached 312 kilowatt. You see it here. With all systems, including port hydrogen injection, the final performance of 443 kilowatt at 7,250 revs was realized. You see it on the map on the top right. Explaining the map with the final restriction. At low engine speed and full load with lambda 1.1, the maximum performance of the original turbocharger group was utilized. Then in the speed range from 3000 to 6000 revs, the permitted peak cylinder pressure of the basic engine restricts the combustion mean pressure. And finally, at particularly high speeds, the very high mean pressure results also in a high exhaust gas temperature. To stay within the boundaries, the output must be hard restricted above the rated power of 7,250 revs. Talking about the injection order per stroke at 7,000 revs and full load, which is shown in the picture below, also with the valve and piston lift. Because of the dynamic effects in the inlet flow, we could start the port hydrogen injection with still closed intake valves, followed by the water injection shortly before the intake valve opens. With slight open intake valve, the port hydrogen injection stops while the water injection continues. Even when the inlet valve is not closed, the direct injection starts and remains open for the entire compression stroke and shortly before ignition. All to maximize the fuel quantity and use additionally mixing effects. We had also to improve the dynamic response, as said before. So not only the maximum power output is important for good drivability, time to boost means an effective responsiveness from low speeds up to high speed is crucial. Hydrogen lean combustion is relatively cold compared to gasoline combustion, which worsens the turbo response. The combustion rich limit is defined by irregular combustion or pre-ignition. So we used hydrogen post-injection into the expansion stroke to increase exothermic reaction, which improves the turbo response without negative effects on combustion and emission. At this operating point, we had a lambda of 1.5, and with the post-injection, it rises up to 1.1. Additionally, we use scavenging of fresh air by valve overlap, which improves low-end torque and turbo response further without the downsides we seen with gasoline lambda 1 engines. The result of these measures are summarized in the diagram on the top right. Under part load at 3000 revs and in transient operation. Without measures, the pressures after this compressor rise only hesitantly in 1.4 seconds. With post-injection, a constant increase to maximum boost pressure of 1 bar overpressure was achieved after only 0.7 seconds, half the time with these measures. The diagram at the bottom right shows the injection strategy with late post-injection, and here in this point only in direct injection mode. Also talking about pre-ignition handling. Hydrogen is highly ignitable in a very wide lambda range and it requires very little ignition energy, which makes it sensitive to pre-ignition at high specific loads. Pre-ignition highly depends on the choice of components, on the combustion system layout and combustion parameters. Some examples which worsen the pre-ignition: judged areas or undercuts in which residual gas can accumulate, then zones that absorb more heat and dissipate it less effectively, there you get hotspots. Then of course the compression ratio itself and the ability of flashing out residual gas. We have from Toyota source a classification which was presented last year here in Vienna, and they divided into backfire pre-ignition, which occurs during gas exchange, especially with port fuel injection, and can be eliminated by calibration parameters. Then we're talking about the runaway ignitions. The sources are hotspots, can be avoided by component layout. And then we have the injection synchronous pre-ignitions, and you see an example on the top right for this pre-ignition and can be avoided by calibration parameters. Finally, we have the sporadic pre-ignitions, and there you have on the right two examples. The middle one is without high frequency components and the bottom one is with high frequency components, and that can be very good suppressed by water injection. Systematic optimization by statistic evaluation during adaptation and calibration is necessary, and we also used structure-borne noise detection for this pre-ignition with the high frequency components. They are typically late in the combustion. Other detection methods are still under investigation. With all the statistic evaluation, we could optimize the cylinder individual water rate to prevent further pre-ignitions. Some words about the hydrogen storage system. The particular challenge was the packaging of the high-pressure hydrogen tanks because of resulting space limitation in a compact race car. The fuel system totally is fully integrated into the vehicle monocoque and therefore optimized for crash requirements. And it consists of 3 carbon fiber tanks, type 4 from hexagon porous, which offers 6.3 kilogram hydrogen at 700 bars. It has a tank volume of about 157 liters and the system weight comes to 130 kilograms. It's proven to the acceleration up to 10 grams per second. On the top right, you see the H2 supply system, which includes Bosch and third-party components. We investigated substantially an active and passive safety concept, for example, where the components are located in the car, and we used an own hydrogen storage control with dedicated software and specific safety measures because of the light and quite reactive hydrogen. That I will explain a little bit on the next page, because our development targets were the safety according to SAE J2578/79. Some words to this SAE. It's a recommended practice, identifies and defines requirements relating to the safety integration of a fuel cell vehicle, including the fuel cell system, the hydrogen fuel storage, and the high voltage electrical system. It is related to the overall design, the construction, operation and maintenance, and may also, in our opinion, be applied for a hydrogen vehicle with internal combustion engine. So, the biggest risk, of course, hydrogen leakage, and therefore we introduced a safety concept based on several stages. First, of course, avoid leakage mechanically by certified components. Then a protect system from leakage with sequential valve system. Maybe some examples for the valve. We have an on-tank valve, or we have on-tank valves, we have excess flow valves, we have pressure relief valves and system isolation valves. We detect the leakage by diagnosis, and we monitor, of course, the hydrogen system and the concentration. And finally, we vent the hydrogen tanks and compartments to the environment. The tanks and the gas control components are separated from the passenger and engine compartments by partition walls to ensure separation and target dissipation of leakage gas to the outside. See on the left side the exit openings on the roof over the separate hydrogen valve system. The high pressure hydrogen tanks itself are also enclosed in the protective shell, built into the monocoque and expelled from the vehicle via the passive ventilation concept, comprising of pipes and vents that you can see on the right, shown with a red dotted line. So coming to the car, to the race car based on the chassis from Ligier. It's designed for a 3.7 liter gasoline engine. It's full carbon monocoque with extensive modification, of course, for the hydrogen. Considers legal and safety requirements, and we did only minor adaptations at the external outline. Thanks to the complete new structure, also with tailored carbon monocoque, a weight of 1,450 kilograms was achieved. And this figure could be further reduced through additional methods. The maximum speed is over 290 kilometers per hour, while the acceleration values are below 3.5 seconds from 0 to 100 kilometers. The fuel capacity of 6.3 kilogram hydrogen leads to approximately 20-minute racing mode, which is equivalent to at least 2 laps on the Nürburgring. Now I want to present you a short film about our passion meets emotion. Back from the emotion, I will finalize my presentation with a conclusion. we as Bosch Engineering has demonstrated together with Ligier Automotive a concept for a hydrogen conversion of a gasoline combustion engine with only small modification integrated in a race car. We reached an equivalent handling and drivability of the sports car and preserved the emotion of a classic combustion engine. Nearby, same performance level with a very lean combustion in a wide load and engine speed range leads also to low nitrogen oxide emissions. The knowledge we gained during the project will serve as a base for future customer projects for motorsport or beyond. Finally, further improvements on hydrogen storage system will be the key enabler for the widespread introduction of hydrogen engine. We as Bosch Engineering are ready to engineer new CO2 neutral high performance propulsion system with hydrogen combustion engine. It's a pleasure for me to thank the entire team of Ligier and Bosch Engineering for the intensive collaboration, the joint effort to overcome all the challenges that came up, and finally the achieved result I've presented today. Thank you very much for your interest, and if you have further questions, please contact me via mail. Thank you.